Good morning, Sushmita. Sushmita, can you hear me?
Hi, good morning, good morning, good morning, Raj.
Yes. Good to see you up and all set up.
Yeah, yes.
So you
So
you seem to be in a good shape right now.
this is all right, right?
Yeah. This is perfect. This is perfect.
Okay. Yeah, great, great. So yeah, I'll be waiting here, I believe. They'll join after 10 minutes, I think.
Yeah. People will keep joining. I mean, you've done most of your job of starting it, opening the gates. Now they will
Yeah,
do most of
yeah,
the work. Don't worry.
yeah.
It's all going to be
Okay.
smooth.
Yeah. So at 8:30, when the session starts, I will stop sharing the screen.
Yes.
About 2-3 minutes before that.
Yes.
Yeah. Awesome.
Great. Don't seem to have your number.
Hey, I texted you. I
No,
messaged you
just one
yesterday.
second.
Yeah.
You write your name as SU. Is it Sushmita? SH
Yeah.
or SU?
No, the official thing will be SUSMITHA. I'll ping you.
Yeah,
Uh,
please, if you can, because I mean, I'm sure I have saved your number, but I couldn't locate it.
yeah,
Okay.
I just pinged you on
Yeah,
WhatsApp. That is.
Thank you. I've got it. I've got it.
Yes. Yeah. Yes.
Great. Chalo,
Great.
have a great day ahead. Call me. Simply call me if you face any difficulty.
Yes, definitely. Thank you, Raj, and
Thank you.
good day to you too.
Yeah, same.
Yeah.
Sushmita, I'm using this ID for Control
Yeah.
Society, the main ID. So whenever I enter the room, it will show as Control
Control
Society.
Society. Yeah, I realized that. Yeah,
Yes,
that's how
yes.
I realized it's you.
Yes. So I would not be changing my name every time I enter. So I just
Yeah.
want to let everyone know. Control Society means me.
Yeah, sure,
I
definitely.
am Control Society.
That is a great name to have, Raj.
Okay. Take care.
Yeah, yes. Good day.
Same to you.
Look on mute. Hello everyone, good morning.
Yeah, hi, Dipsita. I think I joined as speaker, right?
Let me check this one. You are a host, you are a co-host.
Okay.
Yeah.
And I
So
think
you have the same pause as a speaker, a little more, I guess. Yeah.
okay. Yeah, Siddharth will be the speaker, so I think he will join maybe probably closer to the session time, I think.
Sure.
Okay, so I will just wait here, yeah?
Yeah. Yeah.
Okay, thanks.
Okay, so I'll leave this seminar now. I'm going to look at the other session.
Sure, yeah, go ahead.
Thank you.
Hello, am I audible?
Yeah, Madhu, you're audible.
Okay, after changing several earphones. Yeah. Yeah, of course, it picks up some noise, but no problem. At least it's
I don't hear any noise, but
no problem. Good.
I'm just waiting because Siddharth will be the main speaker, so I will wait. I'll turn off my.
Yeah. While we wait for others, I'm generally curious, who is Nirlipta Mohanty? Is he or she around?
Yes, sir. I'm one of the participants actually, but I was just looking through the lobby and I saw the session open.
Great. Yeah, welcome, of course.
Yes,
So
thank you.
you have registered for the conference also, or TIH has requested you to be a participant?
No, they haven't requested me. I just saw the session open in the lobby and I joined it to look through it.
Great. Where do you study?
In College of Engineering, Pune.
Okay, COAP Pune, of course. Are you in the hostel there?
Sorry, sir.
Are you in the hostel there?
No, sir. I'm at home right now.
No, but you're doing undergraduate or postgraduate?
I completed my undergraduate just now.
Okay. So which hostel you were in when you were in, or you were a day scholar?
No, I was in Pune. I live in Pune itself.
Okay, sure. I visited COAP several times.
Oh, okay.
And I've also stayed with my friends in the hostel
Okay.
Block, I don't require. I think F block.
Oh, okay.
Uh-huh. Good, nice. I'm Madhu Belur.
Yeah, yes, hello, sir.
Yeah. So we have two tutorials going on now, one on MATLAB, one on this Technology Innovation Hub. And today are only these two tutorials and 1 hour each of another tutorial. Yeah, so, but those other tutorials will continue tomorrow and day after tomorrow also.
Okay.
So where you already started working somewhere?
Yes, sir. In Immersion, the company right beside COE.
Okay, okay, sure. You were in electrical or?
No, sir, instrumentation and control.
Sure, sure. Yeah. In a regular conference also, I recall that those who come a little early, they start chatting with each other, they interact. Yeah. So good. That is how we are having it virtually.
Yeah.
What an unrealistic feeling overall. Yeah, I wish we all had physical conferences.
Yes, sir, that would have been a great experience as well.
I agree. Yeah. So we have 10 minutes. So let me go to the other room and come and check.
Yeah, hi, Nirlipta. So what does this company do that you mentioned about where you're working?
So actually, it is a process automation company. So in various industries like oil and natural gas companies, then or a pharmaceutical company, the industry needs a process which needs to be automated. It has so that is controlled by DCS, that is distributed control system, which is made by Immersion, and their DCS is named Delta V. So I actually work on the software Delta V, which is developed by Immersion.
Okay.
Yeah.
Yeah, so I'm Raj Babu. I'm a faculty also at IIT Bombay. I also part of this session. So
Hello, so good morning.
yeah, good morning.
Yeah.
Yeah, hi Siddharth. Good morning.
Hi, good morning, Raj Babu.
Yeah.
I will not be able to keep my video on. I hope that's okay.
I think that's okay. Yeah. Pasunuri, I don't know whether I'm spelling it correctly. Are you there?
Yeah, yes, sir.
Pratibha, yeah. You're not that audible. You're a little feeble.
Sir, is it the same now also?
Now it's better. Yeah. So
Yeah.
you are the volunteers for this session, or?
Yeah, yes, sir.
Okay. Yeah. So most likely I may. So you'll be around, right? So.
Yes, sir. I'm in the campus.
Okay. And in this meeting, you'll be there around, or you'll have to go around other sessions?
No, sir. I will be here only.
Okay. So in case if there is something, I will let you know. But if I am supposed to do, so I am kind of playing both the roles. So I mean, mainly the chair role now. I'm not going to present anything. Presentation will be by Professor Siddharth. So
Okay.
I'm only going to introduce the speaker and then kind of moderate the session. So I think I'm planning to start at 8:30. Or hopefully a few more people will join by that time. So the start recording and other things, is it automatically record? Okay, it's automatically recording everything. Okay.
Yeah, yes, sir.
In case if I am supposed to do something, just remind me. Okay.
Yeah, sure, sir.
Yeah. Hi. Good morning, Professor Ramkrishna.
Hi, sir. So everything is sorted with your.
I think it should be because they said so. Siddharth is the other speaker, so he was able to join. So that means, I mean, I think at least for the first session, all are enabled, and the other sessions, I think should be also fine. So.
Okay, good. So just a little brief. So the tutorial sessions will be held like a Zoom meeting, wherein participants can raise their hand, ask questions. So it can be a little more interactive.
Okay.
Whereas the regular sessions, they are a little moderated, that there will be the speakers, the chair, and the questions and all will be moderated, because these are like time bound and we have to make those 20-minute slots. That also for the plenaries we want to do that. But tutorials are a little informal, so we just thought it's better to not that let people type in questions and somebody see it and then answer, and let so you can also just have a little chat with the participants before the session begins, of their background, and also that you can tune your delivery of lectures accordingly.
Sure. Yeah. Thanks. That helps. Yeah.
So I think you can just try out if you are able to mute participants, unmute participants, and so on.
Sure. Yeah. I will. Samay, Pritam Singh, are you there? Yeah. Can you speak a little louder, Samay? I'm not able to hear.
Hello, sir.
Yeah, now you're audible. Yes. So you are, where are you from, and you're interested in attending this tutorial, is it?
So, like, I am from IIT Bombay, and
Okay.
I'm one of the hosts, like, not for this session.
Okay, you are a volunteer, you mean?
Yes.
Okay. Yeah, okay. So I just wanted to try the mute option.
Yes, sure, sir.
So we have a few more minutes before we start. I'm just going to. Poonam Sahu, are you there? Yeah, Siddharth, if you're there, you want to bring up your slides?
Okay. 1 second.
Just to try, so that so there is already a screen. I think this is probably shared by, yeah, see it's shared by Shushmita. I think she's probably another host. So I don't know that you have to unshare before you share, or if you just share, it will automatically override this.
No, I think I was able to overwrite. So is it visible now, my screen?
I don't see it.
Okay, let me try again 1 second.
Okay, maybe I should. I don't know whether I can. Okay.
How about now, Rajbabu?
Yes, it is there.
Okay.
So maybe say that
Slides are changing, right?
Yeah, slides are changing.
Okay.
Maybe until the thing starts, maybe let's leave the other one only there.
Sure. Yeah. So maybe Sushmita, you can share again.
Oh, she's gone. Okay, that's fine. I think it's probably. Yeah, so then you can leave yours only, Siddharth, because I don't see her. She's probably.
Sure. Maybe I can start sharing at 8:30.
Sure, yeah.
Good morning, Professor Rajbabu.
Yeah, hi, good morning.
Good morning, sir. Ashwini here.
Yeah.
Yeah. So, yeah, I'm available online for any help. And if you need any help in the lab, I can reach to the department.
Sure, yeah, I will let you know offline.
Yeah. So, sir, when is the lab session?
It's in the evening. So this is being recorded, so we can talk offline.
Sure. Thank you, sir.
Okay. Yeah. Good morning, all. So I'm Raj Babu. Siddharth, may I ask you to please share your slide?
Sure. Give me 1 second.
Yeah.
I hope this is visible.
Yeah, slides are visible.
Okay.
Welcome you all to this session on IoT, a tutorial on IoT. So I first welcome you on behalf of ICC as a chair of this session, and I'll also be moderating this session. So before we get started, this IoT tutorial has 3 parts. The first part, which happen now, starts at 8:30 and will be presented by Professor Siddharth Talur from IIT Bombay. He will be talking about sensors in IoT. The second session will be at 3:30 in the afternoon, which will be presented by Professor Gaurav Gaspekar, also from IIT Bombay, which will cover networks of sensors in IoT. And in the third and last session, which will start at 6:10 in the evening, we will have a walkthrough or a lab session, which will be conducted by Lohit and myself, where we will show how to put these 3 things together to make an IoT system. So this session is going to be presented by Professor Siddharth. I'll briefly introduce Professor Siddharth. So Professor Siddharth Talur is a faculty at IIT Bombay Electrical Engineering Department. He did his BTech also from IIT Bombay and his MS and PhD from Electrical Engineering Department of Cornell University. Yes, in 2013, he finished his PhD. Since then, he has been with IIT Bombay as a faculty. His research interests are interdisciplinary and touches upon various aspects of electronic system design, MEMS and photonics. So without more, I will now ask Professor Siddharth to lead the session or conduct this tutorial. And also as a point of reminder to Professor Siddharth and also the participants, Siddharth, so it was, I think, Ramurthy said that we could have this a more like kind of an interactive session. So his suggestion was, if there are questions, we can take as and when we go. So I hope that is fine with you. And as we get started, if you want, you can also kind of get inputs as to what kind of participants we have, and then continue with the sessions. So I'll be as a moderator, as a chair. If questions and other things lead to too much of delay, then I will try to moderate. Otherwise, session is yours, and I request Siddharth to please start and continue.
Okay, thanks, Rajbabu. I hope I am audible.
Yes, you're audible.
Okay, and the screen is visible as well, right?
Yes, it's visible.
Okay, wonderful. So thanks Rajbabu again for that introduction, and I thank the organizers also for this invitation. I basically work a lot in various kind of sensor systems in my own research. As far as my own research is concerned, I will highlight only a very little bit about what I do in this presentation. But most of the presentation, I thought I will focus on this theme here, which is how do you perform, but more importantly, how should you interpret measurements and how should you use them? Because I thought that may be of more interest to this community. I assume there are, I mean, because this is part of the Control and Computing conference, I thought maybe this aspect of sensor systems will be more interesting to the participants. But like Rajbabu said, if you have any questions, feel free to raise them during the talk as well. I'll try to keep the presentation itself not very long so that we have more time later for discussion. I will not be able to monitor the chat during the session. So if anyone has a question, just feel free to interrupt and ask. I will not be offended because I'll not be able to look at the chat. So I will not know if there are any questions there.
Yeah, Siddharth, just please 1 second. I think Professor Vidyasagar, are you able to hear us now? If not, may I request Pasanuri Pratibha to get in touch with those who are not able to hear and see if there is something to do with the settings.
Yeah, sure, sir.
Sure. Yeah.
I am unable to hear. So Sagar, I think, is on mute.
Okay.
I think he's on. He should be able to speak now.
Sure. Okay. Yeah. Okay, Siddharth. Sorry. Please continue. Yeah, thanks.
Yeah, no problem. Yeah. Okay. So in this presentation, like I said, I'll talk more about sensors. But before we do that, I'm sure everyone knows what IoT is, or at least maybe you have heard of it before. Maybe in some aspects of IoT you already work on. So let's just get going with the very kind of basic, I will not even call it introductory concepts, I'll just say glossary. We will just look at what some of these terms are and how they are used, and then very quickly we will dive into sensors. Okay. I hope you can see my second slide. I'll just confirm in the very beginning, but then I'll assume the transition happens. So Rajbabu, is this visible? Second slide?
Yes, Siddharth.
Okay, okay, all right. So these are some questions that maybe you can think about. Perhaps you are already, perhaps you already know the answers to all of them. But if not, some of these things we will cover later in the session, and also perhaps through the day, because especially this point number 4 and maybe point number 3. So point number 3, some examples I will illustrate, and I guess Gaurav will also illustrate in the afternoon. But point number 4, maybe you will be able to better appreciate in the third session, which Rajbabu and Lohit will conduct, where they'll show you some demonstration walkthroughs, and you can see for yourself what it takes to build a system, and appreciate maybe that there are some aspects of this that are very accessible. You can get them going very quickly. and some aspects may require a little bit of time. So at least in today's session, hopefully you will be able to see and appreciate the things that you can get going rather quickly. So as far as the definition of IoT is concerned, I have given here what IEEE defines as IoT. So if we just read it out, it says that this is a network that connects uniquely identifiable things. And things is very broadly defined. Any thing is something that has some sensing or actuation capability. So it either does some measurements, or you can control some aspect of the system using this what they call as thing. And potentially this should have some user controllable or user programmable parameters so that you can customize it as well. And this last bullet point is perhaps the more important one, and the one that we will be talking about a little bit more in this talk and perhaps even the later talks today. It is that whatever information you collect using this thing. So if it is a sensor, you are doing some measurements. So there is some information that you are collecting. Or if it is an actuator, then perhaps that thing has some state, right? Maybe it has some alarm, or maybe it has some threshold or some other gating property, right? Maybe that you can control. So I'll show some examples later, maybe where this we can illustrate. But the reason this internet word is in there is because these are all networked objects, and you can control them, or you can read their state information anywhere, anytime, and by anything. So by anything meaning you can hook them up to other systems. So if you already have some data acquisition system, they can be hooked up there. You can keep logging information there. Or if you have a data visualization system, any dashboard that is also connected to the internet, then you can use that to also perform these tasks. And the actuation also can be automated. So you can kind of appreciate that this is like an autonomous system with a lot of sensors and actuators, but then everything is networked. So it's not one system that is deployed in one place. You can have a distributed system. You can have multiple instances of similar systems that are controlled centrally, maybe, or the control can be distributed. So Internet of Things is a very catch-all and a very wide term that includes a lot of different aspects of electronic systems. And there are many applications as well. So here is an illustration that just talks about some of them. Air quality monitoring is something that maybe you have heard of more recently, because around this time of the year, there's always a lot of discussion about air quality, especially in North India. Health, again, I mean, given the times that we are in, I'm sure this again is something, maybe you have already seen some examples of telemedicine, right? Maybe you have had to experience that yourself. I hope not. Maybe you have heard of examples. So all of these, there are many applications here also that are made possible by Internet of Things. Connected mobility is something that's not quite there in India just yet. There are maybe other countries where there are more ready examples of IoT as far as automobiles are concerned. In India, we are getting there. We maybe don't have any examples that I can illustrate just yet. Same goes for this connected homes. So smart homes, of course, it says security here, but there are also a lot of security concerns and privacy concerns, and those are also aspects of Internet of Things that many folks work on. This again is something I think that will gain more traction in India. Presently, perhaps it's of more interest in other countries. And then smart energy and environmental kind of sensing and environmental information gathering, actuation. These are things that are gaining more traction in India. I think the pandemic did accelerate maybe some of the development in this direction, but these are again domains that a lot of people work in, and domains that are going to become even more important in the coming years. And if we look at what an IoT system contains, so I talked a little bit about this already, and I'll talk only a little bit more. Maybe some of these aspects you will appreciate later in the subsequent sessions, or maybe if you are already working in IoT, you have some experience in maybe one or more of these layers of abstraction. In this session, we will mostly talk about the very last layer here, the one that sits closest to whatever it is that you are interfacing with. So the sensors themselves, actuators, we will not talk about in this session. Sensor interface, I had considered if I should cover maybe little bit of sensor interface also in this session, but then because this was for ICC, I thought maybe I'll leave that out. If there are questions, or if you're interested in knowing more about them, feel free to get in touch later. Some of these aspects here, communication more so, and maybe to some extent analytics and services, perhaps you will appreciate through the afternoon session that Professor Gaurav Kasbekar will lead. And maybe all of these, I think in the demo session, you will get a chance to see all of these in action. But there again, maybe some aspects you will see more of. So I suppose analytics is not something that you will be able to, it's not feasible to show it in action in one session and for you to appreciate that also. So I suppose analytics is a topic that requires more time. But then some of these other layers of abstraction you will get to see for yourself in the last session of this track today. So I will now, so I hope at least what Internet of Things stands for is somewhat clear. Like I said, it's very vague and it's very broad definition. So there are a lot of things that come under what we call IoT. I will talk about only some aspects of them, and even today, I suppose you will not be exposed to all aspects. But if you are interested, some of us have worked in different aspects of IoT, more so than what we are going to show in the session. So sensor interface is one example I spoke about. So if there are questions, maybe after the session, if we have time, I'm very happy to have that discussion. So I'll show a couple of examples now, and then we will go and talk more about the measurement and interpretation aspects of sensors that I was talking about. So here are some examples. This smart infrastructure is a buzzword that hopefully you have heard a lot of. So smart, so anytime you hear smart something, right? Maybe not smartphone, but any smart infrastructure or smart building or smart campus. Essentially, at the very least, what that phrase should convey to you is that there are a lot of sensor nodes. So if we are talking about a smart bridge or smart infrastructure, as is this example that is shown here, imagine there are a lot of sensor nodes. So this is one example from some company whose link I've given here. So they have all these sensor nodes that they have connected to the structure. And there are these energy harvesters, solar panels that are also connected. So they gather information, they power the system through this energy harvester. The sensor makes local measurements at the points where each sensor is installed. So this unit will perhaps make a measurement here. This one will do that here, and so on. And then all of these sensors communicate their data to the internet over Wi-Fi using this what is called as a gateway. So gateway is a part of the system that collects information from all these different nodes, accumulates it, maybe does some pre-processing, packetizes it, and then sends it to the internet or the cloud, where it is stored or maybe analyzed further, or you aggregate data from many different such installations and look for trends. So you could do all that level of analytics on the cloud. So analytics, as I said, is perhaps something that we'll not be looking at today. But then analytics is a huge domain, especially in India. I think that is very accessible. So there are a lot of examples. I'm sure you have seen some yourself as well. So this is one example. And anytime you hear any smart structure or a smart building, at the very least, it will talk about something similar, where you'll have some sensors distributed through the structure or through or distributed on whatever it is that you are making smart. You will make some measurements. Now, how frequently do you make measurements and what measurements do you make? Some of those aspects I will illustrate later in the talk with a couple of examples. But you do some measurements, you aggregate those measurements using some gateway, you then send those measurements over to the cloud. So at the very least, any smart anything would stand for something like this. So in my research group, we work on some sensor system projects in this broad domain of structural health monitoring as well. Here I'm showing one particular example. These are, so maybe we'll start with this image here on the top right. These are zinc discs. The disc you see here in the photograph, it's made of zinc. And these are used in reinforced concrete construction. And they are tied together to the steel reinforcement bars. So in India, I mean, this is the most popular construction method of choice, right? Constructing using RCC, this reinforced cement concrete structures. And we all know that these are very susceptible to corrosion, and the lifetime of the structure degrades as it ages environmentally. And those of you that are in IIT Bombay campus must have seen a slew of renovation activity going on, because our campus is 60 years old. So these RCC structures typically have a life of 20-30 years, and then every 20-30 years you have to do major structural repairs. So I suppose IIT Bombay campus is at the stage where it needs that second round of repairs. And it's a very costly exercise. Of course, there are safety aspects that one has to consider, because these are structures you live in, you work in, so you may not feel at ease working in a building where you feel the roof can collapse on your head at any time, right? So monitoring the health of these structures, especially older structures, right, which have been around for multiple decades, is very important. What you see here is an example of something that does two things. It measures how much susceptible to corrosion that structure is, and it also offers some protection. So in that sense, it's like a passive maybe control system, if I may call it that. Zinc is connected to steel here, and corrosion, maybe without going into too many technical details of corrosion, all I'll say is that it is an electrochemical process. So when we talk about iron corroding or steel rusting, iron converts into, it gets oxidized, right? It gets converted into ferrous oxide. So as you can imagine, there must be something that gets reduced as well. So this is like a redox reaction that all of us studied in school at some time. When you have zinc and steel both present in this system, the zinc acts like an anode. So zinc corrodes more so than the steel. So the steel acts like a cathode, and the anode is the one that gets oxidized. So anode degrades, but the cathode does not. So this offers some protection to the structure. Instead of the steel rusting, it is the zinc that rusts, but it is the steel that offers the mechanical strength to concrete. So your structural health does not degrade. But while offering this protection, so in most examples, you will just see the zinc disc just connected to steel, like shown in this figure. But what we thought we will do is, can we monitor exactly how much zinc has corroded, how much zinc is remaining? So we'll get an idea of the rate of corrosion in these type of structures, and then we can say something about the lifetime, right? How long will that structure last if it has that sort of corrosive environment around it. So we use here the principle that's very commonly used in MEMS resonators, you attach this transducer. So there's this here that you see on the top, this square patch. This is a piezoelectric material that's connected to the zinc disc. And using this piezoelectric material, you can excite these mechanical resonances. So here you see two examples. Across the two terminals of that patch, you perform an impedance measurement. And this is the susceptance of that structure versus frequency. And it has two resonances, two mechanical resonances that you see here. This is a simulation. These last two here are experimental results. And the time here is we subject this structure to accelerated corrosion, and we accomplish in 3 hours what it would take about 10 years in the natural kind of environment. So we accelerate that corrosion process, and we see how the sensor measurement changes. So you see the susceptance signature changes. And we have a lot of papers on this type of sensor where we discuss many aspects of the sensor design and the corrosion dynamics and how they affect the susceptance and so on. But as you can imagine, if one can make these kind of impedance measurements, so in this bridge, if you have such protection systems where you can also perform this measurement, you achieve two things. You protect the structure, and at the same time you get a sense of how vulnerable to corrosion maybe that structure is, or how corrosive is that concrete, or maybe if this is in a marine environment, if this is a bridge on in a creek or in the sea, like the sea link here in Mumbai, you can get idea of maybe how frequently you need to do repairs, where are the weak points and so on. So this is one example of how you can do IoT in civil infrastructure. And this broad domain is called structural health monitoring that you see here in the first link. Here is another example. This is also gaining a lot of traction these days, which is called industrial IoT. So if you just search in your favorite search engine for industrial IoT, you will see a lot of examples of what IoT applications are possible in industry. Something that we work on is measuring. So in the previous slide, I was showing you measuring the state of health of infrastructure. But here, imagine you're measuring the state of health of machines. So in factory floors, there are several machines, several large machines. And if any of those goes down, or you have some unscheduled kind of repairs that you have to do, then it can disrupt your production flow severely. So one aspect one way in which it hurts you is you have to spend money on doing repairs if a machine breaks down. And other thing is because the machine is not working, you are not able to produce whatever you had to produce. So you are losing the money on selling what you could have produced. So it hurts you economically in two ways. So there are many examples of IoT where you connect a lot of sensors to such machines and perform measurements and try to assess the state of health of that machine. Typically, you would measure the power consumption, and because we have most machines will have some rotating elements or some moving elements, so there will be a lot of vibrations. And anytime you have some damage or some damage or failure mode is evolving, right? Meaning some it's not damaged, but it is moving in that direction. Then your vibration signal changes, and you would have seen this for cars, for example. So if you have a car or you have been in a car, the first sign of something going wrong is you either hear some abnormal sound or you feel some strange vibration coming from some part of the car where in normal operation it should not have behaved that way. Or if you have appliances at home, fridge, washing machine, same thing, right? Anytime we hear some strange sound coming from these machines, we suspect something must be wrong, right? Air conditioners. So that's a huge area of this industrial IoT called vibration monitoring, and using vibration signals to make sense of the state of health of machines. So in that, aspect of IoT also we do a lot of work. But like I said, my interests are more on the sensor design and the system design. So mostly we have been working on making a very miniature and very low cost sensors that can be used for such applications. And more recently, we have started looking at coming up with inference algorithms, but then instead of doing the inference on the cloud, earlier I said in IoT, you have a gateway device that sends everything to the cloud and you can do inference there. But a factory floor is a very noisy environment, right? Noisy also meaning in terms of the acoustic noise, the sound itself, but also typically these are in large warehouses with metal roofs and some metal walls. So your internet connectivity inside may not be very great. And these are large installations with many, many machines. So you have to network all of them. That can be a significant cost factor also. So what we have started working on more recently is this edge devices. So on microcontrollers, in the last session, you will see some example of maybe connecting sensors to a microcontroller and then sending those measurements to the cloud. So what we are working on is, can we do inference of the state of health of the machine using these vibration signals on the microcontroller itself, and then only send the healthy or faulty or maybe some key vital parameters to the cloud instead of sending lot of very high frequency data. So here you see this is FFT measurement of a time measurement performed using this sensor. But if I have to sample all the way to 1 kilohertz, sorry, if I need to have that much sampling bandwidth, then I have to sample at multiple kilohertz. And then I'm sending a lot of raw data to the cloud needlessly. So I have to then pay for data transmission, I have to pay for data storage, I have to pay for high-speed data acquisition. So all of those costs can be got rid of if we can do inference at the edge. So that's something we are working on. But that's not what I will discuss in this session today. So one more example of where sensors are used, and these two examples, sorry, I said one more, but here are two examples. These two examples you interact with every day of your life. And knowingly or unknowingly, you use a lot of sensors, right? Almost every minute while you are awake, right? Because if you are somebody like me, you're addicted to your smartphone, and your smartphone has a lot of sensors. So here I'm just showing some examples of even the most basic smartphone these days. Even the so-called low-end smartphones that you can buy have these sensors at the very least. And some of the more expensive, more advanced smartphones have even more sensors than compared to whatever I've shown here. And the same is true for a car. So earlier I said that smart automobiles or this technology in automobiles is something where maybe India is not at the cutting edge. However, if you look at any newish car that you can purchase here, the regulatory bodies do require some basic safe sensors be installed in the cars for as safety features, right? So some of them, for example, you have these sorry, I'm not able to see it here. There are airbag sensors. I don't see any of them, any of these sensors you're talking about, airbags, deployment sensors. But airbag is something that's present, at least for the drivers, it's present as a default option in most car models sold in the country. Maybe in other countries, I lived in the US for many years, so their safety regulations are different. You need multiple airbags. If your vehicle does not have airbags for the passenger and rear passengers and in the roof, then the car cannot be legally sold in the country. Unfortunately, our regulations are a little bit lax. But that's one sensor that you interact with every single day. It's an accelerometer sensor, similar to the one that you have for this portrait landscape in your phone. And there are many, many other sensor examples that are used in an automobile that are shown here. So A good system is one where these sensors are operating in the background. That is why we call these things also as embedded systems, because these things are almost invisible. You don't have to be very conscious about them. You don't need to know that, okay, this measurement is being performed, and you don't need to know how exactly that measurement is being performed. What you care about is the inference from that measurement. So that is the level at which we operate when we interact with these systems. But in the remainder of this presentation, I do want to talk about, if you were designing a system like this, then how should you interpret these measurements, or how should you design the system, and how should you design for these measurements. So I will now change gears and talk about those. But before I go there, I want to pause and see if we have any questions. If there are questions in the chat, maybe Raj Babu, if I can request you to read them out. I am unable to see chat.
Yeah, I don't see any question in the chat, but maybe we can just ask. If anyone have any question, please feel free to unmute and ask the question.
Okay, maybe then shall we go ahead, Raj Babu? We'll take a pause again 10 minutes later or so.
Yeah, I think, yeah, okay, yeah, go ahead, Siddharth. Yeah.
Okay, all right. So the rest of this lecture will focus on, like I was saying, these two aspects. So measurements are very important. Most systems that you deal with, you don't ever need to worry about how the measurement is made. If it's a system that you trust, right? I mean, you are buying it from the market, it's a product that sells a lot. So somebody else has done that validation for you. But if you want to operate at the cutting edge of technology, you will be working with new technology that maybe is not validated, and you have to do that validation business, right? So if you are in that position, then how should you make these measurements? How should you interpret them? How should you critically analyze them? That is important. So we'll, of course, this is a very broad topic. Again, I cannot go into all aspects of this in the next half an hour or so, but I will illustrate some aspects which I think can be appreciated in this short amount of time. And there are many more aspects which I will encourage you to explore yourselves also. And the second one is more important, which we'll also touch upon a little bit. So I'll maybe start with the second one and then go to the first one. It is, how do you read data sheets, which is an important aspect for any electronic system that you're, if you plan to design one, or I shouldn't even say electronic system. Anytime you have to design a system from components, and those components have specification sheets or data sheets, it is very important to understand how you should do design with these specification sheets, right? That's something which is unfortunately not given as much rigorous treatment as it should be, is what I feel. Usually we kind of try to guesstimate our way around data sheets. We see that, okay, I need something which has to be 100 millivolt output. Then I see a data sheet which says 75, and I say, okay, it's close enough, right? So we operate kind of at that level most times, which is okay if you're working with very well-established systems where you know that somebody else has done some validation. You find a tutorial online and you follow it, and you kind of put your trust in the person that wrote that tutorial that your system will work. But when you're operating at the cutting edge of technology, when you're making new systems, who will you rely on, right? You have to rely on your own engineering judgment. So that is an important aspect, which I will talk about a little bit, and why this is even more so for more important for sensors. I will illustrate and how that makes it a little bit different, and I shouldn't use the word complicated, but there are some aspects of this. If you don't know how to interpret them correctly, you will get misled and go down the wrong track. as compared to if you are designing, let's say, an analog front end for a radio, right? So when you're working with sensors, there are some more aspects you need to be aware of that I'll illustrate now. Okay, so anytime we talk about, maybe there are some animations, I'll just go through all of them and then talk about it. We'll start with this image. So here, this is again a very generic kind of block diagram, generic kind of graph that shows some output versus some input. So imagine you have any sensor, doesn't matter which one. Let's take accelerometer because we were talking about that for the airbag and phone. So if the accelerometer, so if this were an accelerometer's transfer function plot, it would show the output of the accelerometer versus the acceleration itself, right? And if I have a very good accelerometer, I should have had this straight line in the middle, this one, right? Which is called the ideal linear transfer function, which says that if I have no input, if my input is 0, then my output is also 0. And if I have some input which is full scale, right, it is at the limit of its span, then my output should have enough headroom to be able to tell me the value of the input through this linear scaling function. All right. Why is that linearity so important? Because if my sensor were not linear and it instead were this type of transfer function, then how do I know that every sensor that I make, every accelerometer that I make will have the same transfer function, right? There are billions of accelerometers in use right now while I'm speaking, right? Because imagine every car has multiple, every smartphone has multiple. So if you are a company that's making an accelerometer, you don't want a transfer function like this, because then you have to calibrate every single one before you sell. And calibration is an expensive exercise. So you would like to design for something like this, but even so, there will be some errors. So I'll now talk about some of these specifications here. So the sensitivity just tells you if I have, change in output from this value to this value, how much does my output change? So it's the slope of that transfer function. Let us imagine we have that ideal linear one in the middle here. So the slope of that transfer function curve is the sensitivity. Linearity just tells you how much the actual transfer function deviates from that ideal one, right? So we would ideally like to have very good linearity or very low non-linearity. And the resolution and range. So range just tells you what is the largest measurement you can make, what is the largest value of acceleration that you can measure. And resolution tells you what is the smallest value of acceleration you can measure. Okay, and this resolution is something we will talk more about in the subsequent slides in this session. And the resolution is impacted by some of these things here. One is this offset. So you see here this ideal transfer function, this actual transfer function. When there was no input, when the input was 0, my output, so imagine this line, we extrapolate here. For no input, there is some finite output. Okay, and that is something which not desirable, because ideally I would have liked my sensor to not produce any output if there was no input, but now if it still shows me some finite value, I have to do something about it. So that error is called an offset error. There is some offset from where the output should have actually been. Then there is noise. So noise again is something that all of us hear about in very different contexts in electrical engineering and even in other fields. But when you talk about sensor systems, noise has a certain technical meaning and certain way in which you should interpret it. So I will talk more about that subsequently. But for now, just understand noise as some kind of random errors in the system. And offset is something which is more like a deterministic error. So you measure the offset now and you measure it 5 seconds from now, the offset value may not have changed that much. But noise is something which causes your output to fluctuate randomly. So you measure your output now, you measure it 5 seconds from now, and 1 second from then If you have noise in your system, you will measure very different values each time. Okay, so that affects your resolution, and we'll see why in a little bit. Cross sensitivity just tells you that if I wanted to measure acceleration with this sensor, but the temperature changed, right? Maybe from summer to winter or during the day, right? From afternoon to after sunset. How much does that sensor respond to this other thing which it should not have responded to? So ideal accelerometer should respond to change in acceleration and nothing else. But then if you have changes in temperature, how will that affect the accelerometer? So cross sensitivity to these other parameters, that is something that one also needs to be aware of when you work with sensors. And then there are other system level considerations. Do you need analog output or digital output? To what subsystem is this sensor going to connect? Is it a passive sensor or do I have to power it, right? Is it an active sensor? Then how do I provide power? Does the power quality matter, right? Does my voltage supply stability matter, right? So all those things then one needs to worry about. What is the package? If I solder the package on a printed circuit board and the board undergoes some stress, will it affect the output, right? Does the sensor have stress sensitivity? How big is it? How much power does it consume? How costly, right? All of these are determinants that are of importance anytime you have to design a system. You cannot say that, oh, I like a sensor because it has very low noise. You have to worry about all these other things also. And then you have to judiciously design systems. You will always run into trade-offs. You may find one parameter that is attractive, but another parameter may not be attractive, and then you have to decide, how do you trade off? So we'll see one example in a little bit of what that means. I already spoke about this one. I said that offset is systematic error and noise is random error. One thing which is often not obvious, but very important is that noise is easier to deal with, but offset is not. Because anytime you have offset in a sensor, where that offset comes from can often be very difficult to pinpoint. Noise, on the other hand, even though it leads to random error, the sources of noise are easier to isolate and engineer. So if I know that a particular component in my system is adding so much noise, I can go and do something to that component. But if I have the overall offset behaving in a certain way, it's very hard to isolate that to any one cause or any one component. So oftentimes the advice I give to my students is, if you know nothing else about designing sensors, choose ones that have better offset. Sorry, if you have to use a sensor and design a system but know nothing about what those specs are or how the sensor is constructed, and you are facing a choice between multiple sensors, choose the one that has better offset performance, right? Because the other errors you can still do something about. This last point is maybe not that important for this context, for this session. Noise can be measured in many different ways and reported in many different ways. So some data sheets will talk about RMS noise, some will talk about peak-to-peak noise, some will talk about noise spectral density. So we'll see one example in a little bit. But you just need to, so anytime you're doing a comparison of different sensors, make sure you do apples to apples comparison. Okay, don't compare RMS noise of one sensor to peak noise of another sensor, right? RMS and peak noise refer to two different things. They are related, but then make sure you compare in the same units. So interpretation of a sensor output. So imagine you took some sensor, any sensor, connected it, let's say it's producing analog output. You connected that sensor output, you powered it, and you connected its output to an oscilloscope, and you see a waveform like this. And I ask you to interpret it. It's it's a question that's very difficult to answer because there is no context. Answering this question requires some context on the problem. For example, in this first time time scale here, you see if I average these samples, maybe the offset is somewhere here. and in the next one it has changed to something here. So if I don't know what this time series plot corresponds to, how do I know if the offset changed or if this was measuring, let's say, acceleration, and somebody moved the sensor, so the acceleration changed, and that is why the sensor responded like this, right? There is a lot of what appears as noise, but now again, how do I know if this is actually noise or if the sensor is responding to something which is changing that fast, right? So what is its bandwidth and so on. If I don't have those pieces of information, interpreting something like this becomes very challenging. So you do need additional information. Typically in any system, you will have auxiliary sensors, right? Like I said, if you suspect that the accelerometer has temperature sensitivity as well, then maybe you will add temperature sensors. If you feel it has sensitivity to, I don't know, strain, right? If the printed circuit board undergoes strain, you may have strain sensors. So you'll have auxiliary sensors to gather all this additional information so that you get that necessary context to then interpret this measurement. And at this point, I already said that the offset errors are often harder to deal with as compared to noise. This is a screenshot of how a sensor datasheet will look like. This is an accelerometer, and you see a lot of specifications shown here. Offset and noise, we talked about this now. Here, noise is specified as some kind of spectral density, but then there is also RMS written at the end of it, so it's very confusing. And voltage is specified in units of volts. Sorry, the offset is specified in units of volts. And there is some temperature coefficient of offset that's also mentioned here. And there are other specifications like linearity, sensitivity, cross sensitivity that we were talking about. There is bandwidth mentioned here as well. I have not talked about bandwidth. Anytime we think of bandwidth in terms of a signal, we think of the frequency, the range in which the spectral information in the signal is contained. Whenever you think about bandwidth in terms of sensors, interpret that as what is the fastest change that my sensor can respond to. So if my input, whatever I'm trying to measure, if this was acceleration, if that input were a sine wave at 1.6 kilohertz, then maybe these sensors can still respond to it, right? So interpret bandwidth for sensors in that way. It's the how fast a change can you measure. Okay, it's not quite interpreted the same way as you would interpret bandwidth of a signal. Okay. What I want to talk about is what are these three columns, because these three columns you will see in any data sheet, not only sensor data sheet, but it's important to understand what are these minimum tip or typical and maximum specifications. Most data sheets will have this disclaimer. They will say that the typical specifications are not guaranteed. The minimum and maximum are guaranteed. So if you buy a sensor, you meaning, let's say you are representing Apple, maybe you work at Apple and you are purchasing, I don't know, 1 million accelerometers, and you get a batch in which this spec is violated. Maybe you are getting the sensitivity larger than this value. Then you can return all of those accelerometers to this company and get money back, right? Because this is a guaranteed spec, so it has a legal connotation there. So if these are violated, the min and max specs are violated, then you are eligible for money, your money to be returned. Of course, you and I as individuals cannot avail of meeting. It's very easy to ignore us, but it's not so easy to ignore Apple. So any large manufacturer, right, that or a large customer of any sensor manufacturer will hold these numbers to the manufacturer very seriously. But these ones here are not guaranteed. So then the question is, why are they specified for most of these parameters? Why are min and max not specified? And if they are not guaranteed, then why are they given here? What do I do with them? So those are important to understand. Anytime you take a sensor, and so if you were to go take this accelerometer and measure all of these, I can almost assure you that not one measurement will match what is given here in this tip column. So then it's important to understand where that number comes from and how should you interpret it. So let's do that with an example. So imagine here, I'm not talking about a sensor, but imagine this is for some light bulb manufacturer that has claimed that their bulbs have a certain lifespan. Okay, and they say that the lifespan, so if you take a large number of bulbs and measure their lifespan, you will get a mean of this 2000 hours and this much standard deviation. And you decided to test that claim. So you took 20 light bulbs and you made lifespan measurements and you came up with these numbers. And you plot the histogram and you see that the mean and standard deviation are very different from what this manufacturer has claimed. So there are many explanations that may come to your mind. The first one may be that the manufacturer is cheating, right? Maybe they are lying, maybe they have a defective product, it's not as good as they claim it to be. The second one, if you're more critical, you may also remember that your measurement method may have some errors also. So maybe you need to also look at your measurement method and make sure you are doing what the manufacturer did when they claimed this number and then test, right? It could be that you obtained a defective batch, right? The manufacturer makes multiple light bulbs, thousands of light bulbs, you bought 20. Your test conditions could be different. There are many explanations. And this is exactly what makes sensor data sheets difficult to interpret, because sensors are going to respond to many things and these test conditions are very important. Manufacturing batch is very important. So all of these things you should remember whenever you purchase a sensor and try to integrate into your system. I will not talk about the numbers here too much, but every time remember that if we are going to take a sample like this and plot the distribution of any parameter, if it's randomly distributed, we will, meaning the underlying distribution, if that's truly random, we will expect to see something like this normal curve, this Gaussian curve. And the way you interpret here is that I wanted something which should have had zero deviation from the mean, but then there is a finite probability, right? I could be anywhere on this curve. So the probability that I am in this portion of the curve is 4%, right? Or probability that I'm here is 0.5%. But there is significant probability that I'm here, right? It's 15%. So you should always remember this, that anytime you are working with a large sample, in this case, it would be large number of sensors, you are going to be somewhere on this curve. So that is why I said you will never, almost never measure zero deviation from the tip value. You will always measure something which is deviating from that with some finite probability like you see here. And I'll skip all of the interesting kind of technical details on why this convention, but usually the tip specification may be one of these two numbers, or sometimes if it's given as a range, it may be this limit. The mean plus minus 3 times the standard deviation, because if you are 3 times the standard deviation, you are between this mu minus 3 sigma and mu plus 3 sigma. You are accounting for 99.8% of all possible measurements, right? 0.1% on this side and 0.1 on that side are not accounted for. So tip measurements usually will give you a sufficiently large range. So whatever you measure will fall within that range. But some datasheet manufacturers may only give one number, right? Like here, in which case, if it were noise, maybe they're telling you the mu plus 3 sigma, all right? Or if it is offset, maybe they're telling you, in this case, it's symmetrically placed, right, about these two. So maybe they have come up with some other convention here. But remember, these are all conventions. There are no standards. So typically, datasheet specifications for sensors, because the sensor community is something that evolves so rapidly, right? Imagine 15 years ago, there was no smartphone. Today, everyone has a smartphone. Because this community evolves so rapidly, the standards the standards lag development by multiple years. So then usually you're working with conventions, different manufacturers have their own conventions. So that makes it a little bit tricky to work with. But if you're aware of where these numbers come from, you can do something about it. And on that same token, this min-max specification is 5.5 sigma on either side of the mean. And usually any manufacturer will not only do a certain number of measurements and compute this value and report it. You need to also account for process capability. So I'll just illustrate that with one example here. This has a lot of text, so maybe later if this is being recorded, you can pause and read this in great detail. Just understand what is this CPK definition right now is not important. It has something to do with the process distribution and the datasheet specifications. Definition is not important at the moment. Just let's understand in terms of this car. So let us say you have a sensor that has a distribution which is about this wide, as much as the car. And you have written a data sheet that gives you this as the minimum spec and this as the maximum spec. These specs you cannot violate, the max and the min, because then you have to return money to a customer, right? So if you had this, then that's very nice. Your process is always capable, meaning any car that you make will fit in this garage. But if you have a car which is too wide and your data sheet is too narrow, that's not good, because you will bump the car into this side and you will have to return that money, right? To interpret that way. But what you have to remember is that today you are making a few sensors and making a data sheet based on that sensor. But remember, you are going to make that sensor for tens of years. But you have to still stand by that same data sheet. If you keep updating your data sheet every few months, sooner or later, people will stop buying sensors from you and your company will shut down, right? So you have to make one data sheet which is future proof. So you have to account for variation. So maybe today your car is driving along this line. Tomorrow, it could be anywhere here. Then you have to think of how you are going to set your data sheet limits, right? So ideally you want to be here. So your process distribution over life and data sheet specification should have some guard band designed in, right? So most manufacturers will follow this. Startups, maybe not. So anytime you're buying from startups, you have to be very critical about how their guard bands are set, because to do this guard band setting, you need very mature processes where you are able to do things called as Q lots. You are able to intentionally design sensors that have variation that you expect over the life of the sensor, right? So that is something you have to always remember. And like I said, these problems become even more relevant when you are working at the cutting edge of technology. Today, if you are going to design landscape portrait sensor for a smartphone, you are probably not going to make mistakes because the world has been doing it for the last 15 years, right? Or more. But if you're going to design sensors for problems that people have not tried solving yet, you need to worry about these things. All right. So I'll skip this. I just wanted to talk about how do you, if you are making a few measurements and don't see a normal distribution, then how do you come up with that mu and 3 sigma and all of that? You can leverage the central limit theorem and do that. So you make a bunch of measurements and take samples of those measurements and compute the distribution of the means, right? So take this sample, compute its mean, take this sample, compute its mean. So you can do what are called as these sample means and plot a distribution of those. So the central limit theorem tells you that the distribution of the sample means is guaranteed to be Gaussian, and the standard deviation and mean of that distribution are related to the original distribution. So you can use those to come up with your data sheet number. So that's all I will say about that one. And now I want to talk about this thing, which I will take maybe 10 more minutes to talk about, this case study I mentioned earlier about trade-offs, right? And sometimes it may not be very obvious. How do you choose between two sensors? How do you trade off? So that may not be very obvious. So I'll talk about this because again, I felt for this ICC community, these aspects may be more interesting because maybe you will use this to do some control loop design. So how do you decide on a parameter that you want to sense, right? That may be important. So I'll talk about this, but again, let me pause here and see if there are any questions.
Yeah, so so this is I think we have about 20 minutes or so. So I think, yeah, this is the right time to pass. So I request participants, if there are any questions, please go ahead. Okay, if not, Siddharth, maybe let me just kind of try to just ask some questions with some relevance. So you talked about designing sensors and looking at specifications and so on. So my question is, in the context of IoT, do we benefit, or what do we do to kind of, let's say, look back at the design knowing that this is meant for IoT? Is that something which is being considered usually? Or because traditionally sensors were designed always to operate by themselves, and so we emphasize in all these specifications. Like, is there a way to look at back? Okay, now we are designing sensors with a IoT in mind, which means IoT, basically there are going to be a large set of connected sensors. So here is something we could do in the design or specific. Is there something, I mean, you can mention now, or do you want to take it a little later? I just to kind of get the context.
Okay, so I think your question is that the way the sensor data sheets or the specifications are usually written is for conventional applications where maybe you are using it for monitoring or data logging. But now that we are discussing using them in Internet of Things, do we look at them differently? Is that what you are saying?
Correct. And also benefit from that. Like, can these designs be in a kind of a very high level sense that, okay, here are some additional things we bring in so that these design of sensors or specifications of sensors have these kind of leverage.
Right. So maybe that aspect I will illustrate through this case study, because here, when we finish talking about this case study, you will see that although it appears as a noise versus power trade-off, what you really need to compare is some hybrid specification, which is not given in the data sheet. So you almost need to define your own parameter of interest for this application, which is going to be an IoT application. So maybe this will illustrate some of those aspects. I'm just trying to see from a sensor design perspective, that problem then has to be owned by the sensor manufacturer. So if you're working with a commercially available sensor and trying to design a system using that, then you can do what I'm going to talk about in the case study. If you are designing a sensor and you know that it is going to go into an IoT, then how should you design it, or what kind of parameters do you report to your customers, right, so that they can better integrate it into their IoT. It is a difficult question to answer, because when you are designing a sensor, you would like to, so an accelerometer, for example, has so many applications. So which one do you design for? So typically there are grades. So there are some companies that make what are called industrial grade accelerometers. Some will make automotive grade accelerometers. Some will make consumer grade, which go into our phones. So in these different domains, there are different specifications that are important. So at the very least, you can follow the guidelines that community follows and report specifications. So if you're designing for industrial use case, don't design your data sheet like a automotive sensor. Sure. So maybe that's more relevant if you're making sensors which you would eventually want to sell. But if you're purchasing sensors which you want to assemble into your systems, that aspect I will talk about in the case study.
Sure. Yeah, Ramakrishna has a question. You want to, or at least I see a raised hand.
Yeah, I just have a very general question about. Okay, I'm not from the sensors background, so how would maybe you can tell a few things about the evolution of sensor technology in the IoT setting, because these days there is a lot of things about retrofitting old kind of equipment, say a wind turbine or even an automobile, to make them something like IoT enabled. First, like, is that a good thing to do, or and then what is a sensor which is IoT based sensor and a normal sensors which we used to learn when we were doing our undergrad courses and so on. So just something on that, because I think the analysis part of what you had showed would be invariant of the IoT setting or not. Maybe I'm not from the background, so my questions might sound very stupid or primitive.
No, they're not stupid at all. So the analysis part which I was showing until now will maybe be more apparent why that was useful in this case study. But just to answer your question, that's an important one, because like I was saying, that sensors don't have standards around them. IoT is very similar. There are no standards there. Earlier, I was showing example of this industrial IoT where you have these vibration sensors on machines. And the question you asked is very important in that context, because nowadays the motor manufacturers are making motors that have built-in sensors. So the motor itself will tell you its state of health. But then a factory, so we had visited this Coca-Cola, there is a Coca-Cola bottling plant near Mumbai. It's a huge plant and they want to do something like this. Now they cannot go replace all the machines in their plant with these new machines that have built-in sensors. So they do have to do retrofitting. But then they have to worry about how many sensors will you install, where all will you install? Do you do that on some critical equipment or do you do that everywhere? How will you collect the data? Where will you store the data? Data security, then all the visualization of the data. So all of these things are not always, I will say, not always technical questions, but there is the techno-economic. I mean, you have to worry about the economics of this also. So technology-wise, because this is very modular technology, there are several options. And because the standards have not kept up, there are many more options than there need to be, is what I feel. So your question is very important, because how do you then choose? And most often that ends up being an economic choice. So, I mean, if I were to give a very short answer, I will maybe just say that. But then it's, if you were to actually kind of, if you are facing a challenge where you have to do a system design like that and you are shopping and you are unsure, you know, which sensor to use or which system to use, it's a very multifaceted problem. So usually when I worked in analog devices in the MEMS product IoT organization for some time, that was always a problem. I saw that the customer, the sensor manufacturer, their system engineer, everyone has to kind of discuss together and figure out maybe the most optimal solution, because there are many aspects to that problem. And usually it varies. So I mean, whatever solution may be feasible for one application may not work for another application. So I mean, does that kind of give you an idea of how complex and maybe unorganized this whole thing is? The problem is standards. There are no, or the standards are few years behind, and that is why these choices are not that straightforward always.
And what about reliability of the sensors themselves? I mean, how prone they would be to malfunctioning and.
Yeah, that's another good question, because again, like Raj Babu was saying, maybe they were conventionally designed for one market and now you are using them. You have to keep the data always on, or maybe you are using the data in certain way, right? So data meaning the sensor output in certain way. Most of the reliability burden, so like I said, it requires discussion between the customer and the manufacturer. From my experience working with a sensor manufacturer for some years, I think that burden is borne by both parties. The manufacturer, if it's a key customer, the manufacturer does some additional reliability testing to maybe qualify that sensor for the whatever new application the customer is making. But then the customer also has to own a little bit of the reliability. So take Apple, for example. When Apple first came out with the iPhone, accelerometers were on the market, but they were used as airbag sensors in cars. And now Apple wanted to use them in phones to do landscape portrait. But then phone you would drop, right? Or Maybe if you're not very careful, these days I think we are more careful with phones. 10 years ago, we were not so careful. So the phone will see very different kind of usage as compared to a car. So then the accelerometers have to undergo more reliability testing to see if it qualifies for that application or not. So those are examples where maybe the manufacturer may do some more testing for this customer for this application. But then Apple would also have to do some of that because Apple is trying to come out with a new application that the sensor is not rated for. Yeah, so these are all very case to case. I mean, it varies. The kind of challenges that are involved varies for every different application.
Okay, thank you.
Yeah. All right. So then shall we go ahead, Rajbabu? We have
Yeah, so that I know it. We are kind of getting close to the time, so it's about 43 now. I think it's supposed to start 9:50. Anyway, let's just try to wrap up and then see if there are questions. Maybe we have
I'll take 5 minutes for this.
Sure. Yeah. Thanks.
Okay. So like I was saying, this is an example of how do you handle a trade-off when the answer is not very obvious. So this is the example that I wanted to talk about. So if you have a large communication tower, so this would perhaps fall in that structural health monitoring, and there is some antenna here, and maybe because of this is on some hill, and maybe there are changes in the seismic kind of changes, or wind may cause this thing to change, or maybe there is load on this element and this weakens, right? So there are many reasons why that antenna that needs to point in this ideal direction may deviate from that ideal direction, and we want to detect that. And this is, as you can see, a large structure, so it's not possible to have a lot of sensors installed here monitoring all the time, because this also looks like a remote installation. So we have to worry about power, and what if there is power outage, then what do we do? Maybe it's a critical installation. So the question, so because we are short of time, I'll quickly go through the question and then go through the answer as well. Imagine you had two accelerometers which you could use to do tilt sensing. Okay, so basically like your landscape portrait, it just has to measure the alignment to gravity, and you can use an accelerometer to do that. But you have two options here. One has low noise but consumes a lot of power, and the other has much lower power consumption, but it also has a lot of noise. So you can make XL1 will have higher resolution than XL2, but XL1 consumes more power, and we need something that has very good noise and very good power. So how do we choose, right? Maybe ideally we would have like noise of XL1 and power of XL2, but that is not possible. We have to choose between these two. So do we choose based on noise, or do we choose based on power? That is the question. Okay, so because we are running out of time, I'll just walk through kind of the thought process here. We don't want, so maybe we want the sensor to alert us if the antenna tilts beyond this half power bandwidth range, right? So beyond this value, but maybe we don't want to wait till it actually reaches that limit. Maybe we want to trigger when it reaches a quarter of that value, let us say. And like I said, this we will just look at the orientation to gravity. So we will say that 10% accuracy is maybe okay. These are numbers that are, I mean, there is no good reason for coming up with 10%. You could use any number here. So that is why I called this a heuristic methodology. So basically what we are saying is, if I am okay with 10% accuracy around 25% of that half power bandwidth. So if I want to measure those small changes, then how much resolution do I need? So I can do this simple trigonometry here. This 5.5 is for that peak to RMS conversion that I was talking about earlier. And I come up with this kind of resolution. And then, like I said, if this is oriented to gravity, then simple trigonometry just tells me that my accelerometer can have about this much resolution, 50 microgram, sorry, 50 micro G. But you see here, this is noise, which is specified in units of noise spectral density. So it doesn't say how many micro G of resolution. But one key insight here is that you don't have to do real-time measurement, meaning the sensor need not be on all the time, right? We can maybe do this measurement once every 5 minutes or once every hour or something like that. That maybe is again, how critical is this will determine how frequently you need to do the measurement. But you don't need to keep the sensor on all the time. So power consumption is not something that matters directly, right? We need to figure out how long we can keep the sensor on and average its output so that we get this resolution, and then we can turn it off. So the question really comes down to how long you can average, or how long must you average to get this resolution. Because if we find that value, then the specification that we can compare is this energy per measurement, the power consumption multiplied by that averaging time. So the question is, how long do we average? How do we figure out that value? So one second, my slide isn't changing. Okay. One thing, because we are running out of time, again, I'll go very quickly here, is to realize that averaging may not always help. So if I had a sensor, let's say, so this is a gyroscope sensor example shown here. But if there is no rotation, and if my sensor just keeps measuring this value over time, and I keep seeing something like this, so obviously there is some noise, but you see the offset is drifting all over. So here, if I'm going to do averaging, let's say in this short window here, I'll measure some value of offset. But if I measure over this entire window, my offset value will be very different. So averaging does not always help. You have to judiciously decide how much averaging to do, whether to do averaging or not. And in sensors, typically you have to worry about this drift also. So that is something that is important to realize. This is going to be technically very kind of detailed concept, but there is this one measurement which you can do called an Allen variance measurement to better appreciate how much averaging to do. So I'll just maybe skip through the methodology because I cannot talk about it in 1 minute. You can read this later, or start with Wikipedia. It has a decent enough explanation for what this is. Essentially, it tells you that if I make bins like this and compute the average value in each bin and look at this deviation, right, this kind of variance of that means within each of those bins, then how does that variance vary when I increase my bin width? Okay, and typically you will have a shape that looks like this. So declining slope means that if I increase my bin width from this value to this value, I am getting lesser deviation or lesser variance. Okay, so that tells me that averaging is useful because I can reduce the variance by averaging. But long integration times, or long this averaging time, or what they call as correlation time, averaging actually starts hurting you, because especially when you have drift like what I was showing you earlier, if I make one bin of this size and another bin next to it of that size, then my averages are going to be very, very different. So and if I increase the bin size even more, it's going to increase even more. Okay, so this curve tells you a little bit about how your averaging time and the deviation or the variance in that measurement are related. And ideally, you want to be as close to the minimum variance as possible, and then see how much averaging time gives you that. If you average for any longer than that, then this will hurt you. And typically there are many, so this is again taken from gyroscope literature. There are various types of noise sources that cause various slopes in this plot. The three important ones I would like you to focus on are the negative half slope, which comes from white noise. Flicker noise, I should have written here, the slope 0 is flicker noise, and drift is slope +5. So flicker noise, which is this slope 0, is the one that limits your resolution. So that's something you always need to remember. And this Allen deviation measurement may not be present in all data sheets. So you have to do that measurement yourself. This is one example for what it looks like for that XL1. And XL2 has 9 times higher noise. So the Allen deviation curve is drawn accordingly, 9 times higher. So this is log scale, remember, log scale here and log scale here as well. So the dotted red line would be for XL2. 50 micro G is what we wanted. So that line is somewhere here. So we see that XL2 has to be averaged for about this much time, which is some 4 seconds or so. but XL1 can be averaged for much smaller time, much lesser than 100 milliseconds. So you can do that. So XL1, the time comes out to be 50 milliseconds, and XL2, it is about this 4 seconds, like I said. And then if we do that computation of how much power, how much energy per measurement, which is power into averaging time, we see for the low noise one, it is 17 microjoule per measurement, and low power one, it is 105 microjoule per measurement. So this is the parameter based on which you have to do the assessment. So in this case, the answer was XL1, not because it had lower noise, but the average energy per measurement came out to be a smaller number. All right. So this is one example. There are many such examples, and this is my last slide. So remember this, which I said, that standards are not evolving as quickly as sensor technology. So it requires a little bit more critical thinking and interaction with other owners of the problem, including the sensor manufacturer. And there are many opportunities to innovate at very different levels. So with that, let me stop here. The communication aspects of IoT and the system examples, I think you will experience later today. So thank you all for your attention.
Yeah, thanks, Siddharth. I think we are almost on time, and maybe Siddharth, you can momentarily turn on your camera so people can see you. And if there are any questions, I think there is a session probably starting at 10, and people may want to leave, but I think we could still take few questions. So, and those of you who need to go can please go. Before that, I would just like to thank Siddharth for this talk.
Thank you.
On behalf of ICC and as well as TIH, which is hosting this session, and also as chair of this session, though I'm also a participant and will present like Siddharth later. Any questions at this moment?
Otherwise, participants can always email me. I can take questions offline also.
Yeah, so I think you can find Siddharth Tallur at EE Department, IIT Bombay website.
Yeah. I can add my email ID in the chat.
Sure.
Yeah. So I've added my email ID. Anyone that has questions, feel free to email me.
Okay. The last time, any questions? Okay. No. Yeah. Thanks, Siddharth.
Thank you, Raj Babu. Thanks, everyone.
Yeah. Thank you all.
Good day. Bye.
Bye.